So, hello, I'd like to introduce Tomas Boros. He has his own project, EdgeCDN, and he will introduce you how he looks on CDN by his own eyes. So, stage is yours.
This one is okay. This one's working as well. Okay, thank you very much. So I'm going to start my presentation with this statement. If you were here on the first day at the keynote speech, it was mentioned that Kubernetes is a platform for building platforms, and I very much agree with that. If you just look at the broad ecosystem of the CNCF landscape, you have amazing amount of applications and orchestrating platforms to use on top of Kubernetes. If you want to run PostgreSQL databases, you can take the cloud native PG operator and you can pretty much easily manage PostgreSQL clusters on Kubernetes. If you want to manage your rollouts, your applications, or even rollouts application remotely from a single point, you can use Argo CD. If you want to manage Kafkas, we had just a talk about that recently, you can use Trimzy, and even you can provision cloud resources with Crossplane. Although you can end up in a situation where I was at one point, where none of those tools actually fit my use case. So I decided to build my own operator. And how do you do an operator? A controller, it's pretty easy. You have to define a few CRDs. You build your controllers, and you hope you know what you're doing, and it's actually doing what you're supposed to do. So a little bit about myself. My name is Tomas Boros. I'm a DevOps engineer. I work for a small Dublin-based company for several years now. I have a background in research. I did some research on CDNs and video streaming, especially on MPEG Dash. And I used to work as an external contractor for Slovak Telecom and T-Mobile Czech Republic. And I was in charge of building the CDN platform for the Magio Go OTT platform and live TV. Just a side note, this platform is quite huge, running around on 80 servers, and currently is reaching around 3 terabits per second in an aggregated maximum throughput around larger events like football or hockey matches. And since I no longer work on the project, I decided I'm going to join my know-how and my expertise on CDNs and DevOps. And I decided I'm going to build a CDN on my own. And of course, the obvious choice was Kubernetes. So just a few slides on what a CDN is. CDN is basically a distributed network of servers distributed globally around the globe. And it helps you to deliver the content to your users faster and more efficiently. It reduces latency to your origin servers and overall improves the user experience. And it is doing by storing a copy of your content from the origin server. So for instance, if you have users in this use case from US downloading an image, a video, or whatever content from your origin, the user is not sent to the origin itself, but is sent to the closest cache. And if the cache contains the given content, it delivers it to the client. If it does not, it will first fetch it from the upstream, and it will honor the cache control headers from the HTTP response and will cache it accordingly and then serve it to the clients. So in such use case, if you have millions of users requesting the same content, all the content will be served from a cache itself, so you are essentially reducing the load on your origin massively. And how the actual routing is working in a CDN. How do you decide where to send your users? So in most of the cases, the redirection is DNS-based. You ideally want your DNS to be behind an unicast IP address, and it works in a way that whenever a request comes in, the DNS server looks up your IP address, and it tries to make a perfect decision based on your IP address, and will redirect to you to the closest DNS server by sending you an A request on a AAA request response, to the cache with the IP address of the cache which is closest to you. There are also some alternatives. You can also use HTTP Anycast. So essentially, you are just redirected to any of the cache servers directly with an HTTP Anycast IP address. This has some drawbacks, and at some point, also 302 redirection methods were used as well. I would say it's not really common to use that anymore. That works in a way that first you send your HTTP request to one of the routers, and the router will send you a 302 redirect to the closest cache. This has a bit of an advantage because you can address, you can take into consideration way many more parameters, how to do the routing decision, for instance, the user agent, the content itself you are requesting, although it has an extra round-trip time because first you have to do an HTTP request to a router, and then you do another request to your cache itself. And why did I decide to build it on Kubernetes? First of all, because I worked with Kubernetes for a couple of years, and I know the platform well. Kubernetes itself offers a very reactive control plane thanks to the Kubernetes API. The tooling is great, and you can easily extend the API. The solution itself is Ingress-based, and it has a first-class support for certificates with Cert Manager, and there is a DNS in Kubernetes available. You all know the CoreDNS, which is actually pretty easily extensible, and I will get into details of that. And how the control plane works basically in Kubernetes. In the end, everything in Kubernetes is essentially a controller. And what the controller does, it is basically just continuously compares the desired state to the current state. So whenever there is a change to a given resource, an event is fired in one of the components, and the reconcile loop will try to get that resource to a desired state. So for instance, if you create a deployment, the kube, you do a simple kubectl apply of whatever YAML file specifying a deployment. It will be picked up by the kube control manager. The kube control manager basically will see this information and will create a replica set that is going to be picked up by the kube control manager again. And then it creates a few pods. The pods are then picked up by the scheduler. The scheduler chooses the right node to schedule the pod on. And whenever it found a suitable node, the kubebot locally on the node itself will pick this information up and start a container, either with containerd or some other containerization system. All right, so as I mentioned, you can extend the base functionality of Kubernetes by custom controllers. So you have to define those CRDs, and those controllers are basically then just reading the Kubernetes API. They use an email stream through informers. So every time there is a create, update, or delete event happening, the reconcile happens. And your controller basically is responsible for getting the resource into a desired state. So for this tool chain, I decided to use KubeBuilder. It's a Golang-based tool chain for building Kubernetes controllers. I've included a link down there if you're interested to check it out. And for distributing the configuration over the platform itself, I decided to go with Argo CD. It supports a multi-cluster architecture, which means you can manage multiple Argo CD clusters from a single central point. So a little bit of insights. So basically, every single node in this CDN platform is a Kubernetes cluster. So the control plane runs in the middle. That is responsible for configuring the whole platform. And every single cache or DNS server basically is a separate kube cluster, which is onboarded to the Argo CD on the control plane. And you can annotate and define a few labels on those specified clusters. So you can give certain roles to those clusters. In this way, you can decide whether this node is going to be a caching node or whether this node is going to be a DNS node. So these are the CRDs which I have defined. Very few ones. I will go to the next slide because there's more in details. So I have a location. I'll have a location CRD which identifies the endpoints. It manages node groups, and it defines also the geo routing. Each and every location, basically, it could be, for instance, Prague or Bratislava or Europe or whatever. And you can define multiple nodes in a single location, and you can also specify which geotext should the CDN route to. You can define prefix list. This is useful if you eventually would like to use any static routing, or this is also a sort of a preparation for an eventual BGP listener. So for instance, if you want to place a cache into the network of a specific ISP, and you exactly know which prefixes are do belong to this ISP based on ASN number or the prefix list, you can low feed those prefixes into the routing system as well. The project is simply just a UI feature for grouping customers to enable multi-tenancy and projects. The services itself are the services that you roll out. Here you specify basically the domain names, the upstreams, what kind of caching mechanisms, what kind of cache control. We will get into details as well. And you can define some zones. Zones are basically delegated subzones, DNS zones. So you can onboard your own domain. So the platform itself works with a predefined domain, but at the same time, you can specify an external domain which you can delegate with NS records to the CDN platform. So in action, if you create a service resource, I have to mention that this is not a standard service, which you know in Kubernetes, but this is a services.infrastructure.edgecdn-X.com resource. If you create a resource like this, the controller on the control plane picks it up. It creates an application set, and the application set ensures that this service is basically distributed to all the endpoints over your CDN cluster, and it also handles the certificate management. Whenever this service gets created on a cache node, the controller runs there as well, but in a slightly different configuration. So it picks up the service. It creates a service which will point to an external service which you have configured as an upstream, and will create an ingress with a bunch of custom annotations. So it can also not just forward the request to your upstream, but at the same time also cache the content. I would like to add that the platform also supports S3 origin types, and currently it is solved by just simply deploying an Nginx S3 gateway pod, which is essentially can connect to an S3 bucket, and you can use it as an upstream for your CDN. And whenever a location or a service is created on a DNS node, when a location is created, it is loaded into CoreDNS, and a probe is created for doing health checks, and the service just basically just resides there, and no extraction are taken because it is only needed by the CoreDNS itself, so it can respond to those requests. Okay, this is how the service looks like. You can specify the caching layer. In this case, it's an SSD cache. The domain name, basically, which CoreDNS will respond to, and also the Nginx ingresses will respond to, and the static origin configured. In this case, it's testorigin.dbiotech.sk, which is my testing website, basically, for this project. And you can define WAF and then a few other things. So the next part was basically the CoreDNS. I had to make sure that the CoreDNS can work with those CRDs. So instead of trying to generate the correct configuration and reload CoreDNS every time, I decided to build a plugin. And the plugin is, I would say, pretty mature and pretty cool, and it can do all sorts of things. It can route your request based on static prefixes. It can do geolookup as a fallback if there are no prefix configured. It can, whenever it finds a specific location where the clients should be redirected, and there are multiple servers available in the given location, then it does consistent hashing. So it makes sure that for the same domain name, you always end up on the same server just to make sure your cache hit miss ratio is as high as possible. Whenever there are no nodes in a given location, it can do fallback routing. So for instance, if there are no nodes available in Bratislava, you can fallback the request to Prague, for instance. And the two cool features which I really like, you can also specify for those specs Prometheus alerts. So let's say you have 5 servers in a region and your maximum throughput capacity is 100 gigabits. And whenever the location is getting close to 80 gigabits, you can fire an alert that please do not send new requests to this location anymore because I might get into congestion. And of course, it is doing active health checks. Yeah, so these are a visual representation of those routing features. On the right side, it's simply just routes to BTS, which is Bratislava, just routes the request based on GeoLookup tags. The one on the bottom is basically the same defined for Czech Republic, although the nodes are unhealthy. So it has a fallback specified to Slovakia, so it goes back to BTS. And on the left side, it has a nodes server running in Frankfurt where I have defined a random prefix. So whenever there is a request with that prefix coming in, then it will be routed to Frankfurt. Okay, so these are the CRDs which CoreDNS work with, the prefix list on the left. I'm not sure if the one on the right is readable, but I can show you later on Argo City how does it look like, but basically I can define the GeoLookup attributes and I can allocate a certain weight to each GeoLookup attribute. Here in this case, I have EU and Africa set with the weight 1000. And so basically on routing decisions, the request goes through all these geotags and all these locations. And whenever you get the highest weight, you will be redirected to that node. If you end up in a situation where there are multiple locations candidates with the same weight, then you can still do a weighted round robin, basically. Okay, and to make sure everything is dynamic and fast in this platform, the CoreDNS and the health checker components are basically using Kubernetes informers. The informers are treated as an event stream. So in the background, what an informer does, it connects to the Kubernetes API, does the initial get of all the resources, and then starts watching all the changes from that point. So Kubernetes snapshots and versions the state of every single resource. So essentially, you are ended up with an event stream, and whenever there is a change, the changes are automatically reflected in your application itself without having to reconfigure having to reload the application. And there is also one note which I need to add. If you have many, many, many resources on your Kubernetes API, to fill the cache takes some time. So you can check if the event stream is basically already up to date with whatever you have in the Kubernetes API. And if it's up to date, then it will start serving requests, and that is solved by hooking in the readiness probe basically into this component. Okay, and on the caching itself, it is built, I would say, unfortunately, still on Nginx ingress. I know it's deprecated already. It does support multiple tiers, so you can have multiple node types in a single location. You can have SSD servers for your stairs, RAM disks, etc. You can configure certain key modifiers. Like if you look at the example here, it's the image.jpg with a query param with 124 and with 2048 will essentially give you a different result. So you have to specify that key as a, you have to whitelist that key and it will be stored in your cache key basically. As I mentioned already, it supports S3 origins, and if you want to serve private content, you can enable the URL signatures. That is pretty much standard with S3 and whatever other sort of CDNs, if you have worked with, to access a certain content, you have to sign the URL. If you sign the URL and the URL is valid, you will then get a session token. And whenever then you request subsequent request with the session token, you will be authorized. And the session token is eventually renewed on 60% of the validity of the lifetime. And I was playing around a bit of performance. I just already mentioning here that the platform is compatible with SR-IOV. SR-IOV stands for single root I/O virtualization, which is basically where you need a network interface card, which has this feature. And with what it can do, you can get a virtual function for your physical interface and put it into the Nginx pod itself. And this way you are going to bypass the CNI itself. So you should not consume unnecessary CPU resources on traffic routing and the networking management. And eventually, what's going to be the future of this project, since Ingress Nginx is deprecated, probably I will write my own controller for a different caching engine. I haven't decided that yet on which one. Probably I will go with Ng. It's a fork of Nginx pre-F5 acquisition because it contains a lot more and many modules that are basically now behind a paywall on F5. And of course, it has a very basic analytics and monitoring standard on Elastics on the Grafana Prometheus stack, and the logging is basically done with event streaming. So all the nodes are shipping their logs to the central point, and I'm running basically a simple stream processing application that basically aggregates the logs, and we get very basic statistics, how many megabytes or gigabytes were uploaded, downloaded for a certain service, so we can see what our actual usage and what our actual savings are. All right, I will continue on the demo from here. I do have some backup videos just in case, because you know demos always go wrong when you are doing it live. Okay, so this is how the parent currently looks like. The portal is actually live, and you can give it a try. It's running at portal.demo.edgecdn-X.com. Feel free to sign up. Feel free to test it out. The demo environment, unfortunately, only is running 2 locations because of the cloud costs, of course. But it's just more than enough for demo purposes. So it is OIDC enabled. Once I log in, I can look up the available locations. As I mentioned, I have one in Frankfurt, which is healthy. And there is one node specified with this IP address, and it has a single node group. And in New York City, I have 2 node groups, 2 nodes, and this is the geolookup config, which is configured for this service, for this location, sorry. So Antarctica, how to say in English? And North America, Oceania, South America, and Asia is basically routed to this location. I have the defined prefix list. So whenever there is a request coming in from this prefix, the request will be routed, in this case, to New York City. And you can also define some zones, which I mentioned, and also the customers can onboard their own zones by specifying it on the project dashboard. So now I'll do a quick demo. If I open this project, I'm going to create a new service. I'm going to call it KCD. It will be a static origin type. I have to set an upstream URL. And for that, I'm going to use this test origin, which I mentioned in the presentation as well. I'm going to set it to an SSD caching tier. I'm not going to set any query params and not going to set any paths because I just want to basically forward to the upstream everything under slash. And I submit it. Once submitted, it gets created on the Kubernetes control plane, and the certificates start issuing. And if I look into the Argo CD endpoint, you can see that there is already an HTTP challenge exposed for the certificate. One thing I need to add that getting the HTTP-based certificate issuance was a bit tricky here, because in a CDN you can essentially end up on any of the nodes. So you don't end up on the node where the service itself is configured. So the controller is managing that whenever you get the token from Acme, from the cert manager, which you need to expose, the challenge is copied to each and every node around the CDN cluster, basically. So this way, the token is exposed everywhere. So whenever the request or whenever the challenge request is coming from US or EU or whatever else, you will always get the desired token. And this way, hopefully, the certificate will get issued. Yes, the certificate is already valid, and we can see that the platform is configured, and there is domain name, which I was assigned. And if you open DNS checker, let's wait a bit. If you open DNS checker and you test if the domain resolves, you will see that requests coming from the US ends up on this server, and requests coming from Europe ends up on a different server. So the CoreDNS, the domain names, the ingress, and everything was configured literally probably under a minute, including the certificate issuance. So if I would like to further do some tests, and then I also want to show you that it actually works. So this is already the test website, which is now proxied through the CDN service. And of course, I have some pictures of cats. That's something you always need. And if I should have done this, hold on. I'm going to do this way first. So I'm open a different site, and you see at random content, you will see in the status that it's a cache miss, because this is the first time I'm accessing this website. So right now, if I do a refresh, my content is coming from the cache itself, and it's a cache hit because it was already stored in the cache itself. And one more thing I want to show you. On the right side, I have the logs from CoreDNS running, and I have a nice script which I can show you the routing, how does it work. I'm testing it with a different domain, which is onboarded in this platform as well. So if I do this test, it will just simply do NS lookups against this domain name, and will basically print out on your screen what is the response. So I did a request to cdn.tbiotech.sk, and I received an IP address of 74.220.31.138, which is the one running in Frankfurt. And why did it happen? Is it readable on the site? Or should I make it bigger? Yeah. So as you can see, the geo lookup kicked in. There was a question for this domain name, and based on the geo attributes, the request was assigned with the score of 1,000 for Frankfurt C1, and there is a server running in Frankfurt C1, so I got this response. In the next test, I mentioned to you that you can specify some prefixes. DNS actually has an extension which is called EDNS0 subnet. It is because if you use a resolver, for instance, 8.8.8.8, or whatever else, that which can, even though you are based in Prague right now, the resolver can run somewhere in Germany or wherever. So what you can do is basically the resolver can inject the source IP where the resolver received the request itself, and can pass that information down to your resolver. So if I do the very same dig command, although I specify this plus subnet, if I specify this subnet as well, that I'm mimicking that basically I'm coming from this source IP, and the CoreDNS will first look into the DNS subnet. If that's present, it will route based on that. If it's not present, then we'll fall back to the source IP it received the request from. So in this case, you can see that the v4 static prefix was matched, and I'm routed to New York City. And in the last test, first, I'm going to kill my pods in Frankfurt. The pods are killed. And within a couple of seconds, if I manage to catch that, I received an update, which means that the health check failed, and my health checker patched the CRD with this information that the health check, that the node is down, and that information, thanks to the informers, were automatically reflected in the CoreDNS configuration itself on the fly. So here you can see I was supposed to be routed to Frankfurt, although node is not healthy, and there are no healthy nodes from this location anymore, so it's doing a fallback routing to New York City. So I ended up being redirected to New York City. Of course, in real life, this is not really a useful use case. You would rather route somewhere closer, but I only had 2 nodes, so I don't have any choice. But sometime later, whenever the pod comes up, the pod should be healthy again. So if I do the very same request, now I'm getting routed to Frankfurt because the pods are alive again. And yes, I think pretty much that's it. I'm glad the demo went well. And let me just finish the few more slides I have left. Yeah, I just want to do a quick summary, basically. So this is more or less still a hobby project. It's not really deployed anywhere in production. I managed to build a full CDN capability based on top of Kubernetes. I have right now a POC deployed at Lyrid.io. They are a small Heroku alternative, mostly operating in Asia. They were interested in the project itself, so they have a POC, but currently no actual production running. And the portal which I showed you, which is present on this website, I will be happy if you give it a try. And of course, if you are interested in the project or would like to take a look, would like to collaborate, or if you have an interesting use case or you work for someone where you think a CDN would be suitable, I'm very open to collaboration. And you can find me here, and that's it. Thank you. All right, so the first question is, can you explain again how do you match packet source IP address with a prefix list and the EU-US tag? Okay, so there is a chain of routing, basically. First of all, the source, the prefix lists have higher priority than the GeoLookup. So if a packet comes in and there is a prefix defined for that IP address, then it will be routed to that location. If there is no prefix, then it will fall back to GeoLookup. Okay, next time, what about Gateway API? Are you planning to move from Ingress? Yes, I'm planning to move from Ingress, but probably not to Gateway API, but as I mentioned, probably to writing my own controller based on Ng or Varnish or other caching engine. Technically, yes, but whenever, if I would get to a point where that CDN could start growing, I mentioned that I'm planning to add a BGP listener, which you could do that for me. So it would just run as a listener and ingest the prefixes which the specific ISP wants to route the prefixes to. And those prefixes just simply will be copied over to the Kubernetes API, and then the CoreDNS will itself do the routing. And next one, what would be the main motivation to run my own CDN? Running your own CDN makes sense only at a certain point, and I would say you need to be consistently at least streaming or delivering content at least at 10 gigabits per second. Otherwise, the cost will never, it will be always cheaper to run a managed solution, basically. And if you are an ISP and you have an IPTV, the use case like Slovak Telekom and T-Mobile Czech, they really do have a use case for a CDN. Just for information, I did run the numbers based on the traffic they are delivering daily. If they would use Cloudflare or other solutions with the standard pricing, so they could probably negotiate better prices, but I did the numbers with the standard prices, they would be paying around 100K per day for the CDN. Do you have an example? I do have an example, but I cannot show you here. If you go back, if you find me on the socials, I have a YouTube channel and I have a video on that, how do I configure that. Timescale DB is not used for access logs. Timescale DB is only used for the aggregated data for calculating basically the received and sent bytes over time. Well, I'm not running bare metal right now. And honestly, I probably would not use any, I would probably just use a simple host path. And I would probably use a cache in RAM disk itself if there's enough storage, and probably do an LV cache to a larger storage and SSD underneath. Yes, this was mentioned. I do rely on EDNS client subnet, and I don't really think there's anything better than that, unfortunately. And as I mentioned, if there is no EDNS client subnet available in the request itself, then it falls back to the source IP of the DNS request itself. Yeah, the next question. This is a very good question. I can actually, it is very hard to find a hyperscaler or a hosted CDN, a hosted Kubernetes solution which you can provide you with a load balancer which preserves the client IP. So Azure and AWS can do that because they have their own funky networking stack. But for instance, I'm running on Civo, and I've talked to several engineers at Civo asking if they can preserve the source IP address of the DNS request on UDP, and unfortunately they cannot. So I had to fall back by running a VM next to this Kubernetes cluster, running Docker with a public IP.
Thank you, Tomas.